So, hi guys, am I audible? Just let me know if I'm audible and my screen is visible. Yeah. So, how was the contest? Okay, so today we'll discuss all the problems from the div 3. Okay, so let's get started. Okay, so hi guys, this is Abhinav Kumar and this is TLE Eliminators. Welcome to the post contest discussion of the Codeforces Round 1054. So let's begin with the first problem. Okay, so you are given an array A of n elements where each element is equal to -1, 0 or 1. In one operation, you can choose an index I and increase AI by 1. That is assign AI as AI plus 1. Okay, so you can just pick any index and increment its value. Operations can be performed any number of times choosing any index. The goal is to make the product of all elements in the array strictly positive with the minimum number of operations. That is, product of all elements should become greater than 0. Find the minimum number of operations. Okay, so basically you are just given an array. You are given an array containing just zeros, one and minus ones. Okay, so the elements of the array are either -1, 0 or 1, only among them, no other element. Now what you need to do is you need to convert this array, you need to apply some operations in this array so that the product of this array becomes strictly greater than 0. So when is the product of some numbers strictly greater than 0? What is the condition for that? First of all, if there is any 0 present in the array, the product would become 0. It would not be strictly greater than 0. It would become 0. So first of all, there should be no zeros in the array. That's the first condition. Second condition is, if all the elements are non-zero, then the product will be positive or negative. How is it decided? So I hope you know, if there are odd number of negative elements, so any two -1 into -1, this would give us 1. So any two negative elements make a positive. So if the number of negative elements is odd, then we can say that the final result would be negative, else the final result would be positive. So basically what we need to make sure is that in this array, first thing that we need to make sure is that there should be no zeros. Second thing is that there should be even number of -1s. So how do you do this in minimum number of operations? Now, since the array just contains -1, 0 and 1. Okay. So first of all, whatever zeros we have, you would have to convert all of them to 1, because only operation available to you is increment the value. So you can never decrement the value to make it -1. You can only increment it. So zeros would necessarily have to be converted into 1. Okay, so one operation would go in converting all the zeros into 1. So for every 0, one operation each. Next, whatever -1s you have, if there are like even number of -1s, no operations are required. They all would neutralize each other and make it positive. And if the number of -1s already present is odd, then what we would have to do is just select any one -1, do a +2 and convert it into 1. We would have to convert any one of the -1s into 1 in order to have even number of -1s. Just converting any one of them would be enough if they are odd. If they are even, then let it be. So two operations would be required for that. So basically what we can say that our final answer, the number of operations, is the count of zeros in the array. So for every 0, you would require one operation, plus either you add 2 or 0, depending on if the number of -1s is odd, then you add 2, otherwise you add 0. Okay, so that you can decide, where that you can count the number of minus ones in the array, and you can do a +2 if it is odd. That would be my final answer. I hope this problem is clear to you all. So we can move to the code for this. Okay, so we take the input and then we count. If there is a -1, we do C++, so C stores the count of -1s, and if it is not -1, then I add to the answer 1 minus AI. So if it would be 1, it would add a +0 to the answer, won't affect the answer, and if it is 0, it would add +1 to the answer. So basically for every 0, we do a ++ to the answer, and if the count of -1s is odd, we do a +2 to our answer and print our final answer. Okay, I hope this is clear to you. Time complexity for input part, it would be order of n. This for loop runs n time, and then just printing the thing. So time complexity is order of n, space complexity also input array of size n, that's what the space it takes. Okay, so I guess we can move to the next problem now. Okay, so let's move to problem B. According to rules, participants are paired. Okay, so the problem is here. Petya has an array of n integers a1 to an. It is known that n is even. Petya must divide the participants into exactly n by 2 pairs. Okay, so out of the n integers that she has to divide it into n by 2 pairs. So every index can be, each index can be included in no more than 1 pair. So you have n numbers, just form n by 2 pairs using every value just once in any one of the pair. So when you form these n by 2 pairs, for each pair, its difference is the mod of x minus y. Petya wants to form unconventional pairs such that the maximum difference among all pairs is minimized. So you have to basically minimize the maximum difference among all pairs. Determine the minimum possible value of the maximum difference. So this is the problem. Let's take one test case. Okay, this is an array A given to you. After that, what you need to do is, n is 4 here, so you would form n by 2, which is 2 pairs. So either you can do something like form this pair and this pair. This is one possibility, 10, 1, 2, 9. Okay, or what you can do is maybe select these two and these two. So that would be 10, 9 and 1, 2. Okay, what other can you do? Maybe you can do like this. Okay, that we already did. Yeah, 10, 1 we had done. So this pair would be 10, 2 and 1, 9. Okay, so like for this case, these are the three possibilities. If you look at all the possibilities here, what is the difference? This difference is 9, this difference is 7. The maximum difference is 9. For this difference is 8, this difference is 8. The maximum among them is 8. For this difference is 1, this difference is 1. Maximum among them is 1. So among all the three possibilities, the minimum of the maximum difference is 1 here. So your final answer for this case would be 1. So you can see for second test case, our answer was 1. Okay, so I hope you would have got what the problem is. Now, how do we solve such a problem? So first thing to notice here is, if you look at the array, we just need to find n by 2 different pairs. So the order in which the values are present in the array, that does not matter. We just pick any two elements, and form pairs. So whatever array is given to us, we can shuffle that array and the question remains the same. The problem would not change. So basically, first thing what we can do when we can recognize such type of thing in the question is sort the array. So if we like look at the question after sorting the array, then we can maybe conclude something. So if you sort this particular array, you would get 1, 2, 9, 10. Okay, now sorting the array doesn't change the problem that we have proved, because we just need to select any two elements. Their index doesn't matter. Now after sorting, let's try what would be like the most optimal way to search for the minimum of the maximum difference. So what is like maximum difference? So in the sorted form, let's say if we take this pair. Now when the array is sorted, whatever two elements we select, their difference would be the greater element minus the smaller element. Okay, whichever element is to the right minus to the left. So if you start with 1, you reach 9, this difference would be 8. If you start with 1, you reach 10, this difference would be 9. And if you start with 1 and you reach 2, this difference would be 1. So obviously for 1, the minimum difference it would give would be the element just next to it. 2 would give the minimum difference for that. For 2, the minimum difference would be either just the previous element or the next element. This would be 1, this would be 7 here. For 9, again it would be either just previous element or just next element. So basically we need to just minimize the differences. So in order to minimize the differences, it would be like always optimal to select adjacent elements. Through that we can minimize the difference. So one way of selecting is just select first two elements, next two elements, next two elements, next two elements. Just select two adjacent elements and pair them. But would this be the most optimal answer? Let's say that I'm telling that this is the most optimal answer, this pairing. Can you prove otherwise? So if we try to think that there exists some other way which is more optimal, then maybe for one, if you are assigning anything other than 2, let's say you are going over and assigning like this 10, and then you are pairing 2 and 9, you are keeping these adjacent. What you need to minimize is the maximum difference. So here, if one pairing is inside another pairing, this difference would definitely be less than this. So basically this difference is only going to be our maximum, which matters to us. And you can see that we have like increased this maximum to a farther value, which could have been reduced to 1 to this difference and this difference. Both of these differences are less than this total difference. Okay, even if you try 1 to 9, then this difference and this difference, this is greater than this difference. And if you're picking 1 to 9, you would have to pick this again is greater than this difference. So whatever you pick other than this pairing, you are just increasing the maximum difference if you are picking any of them. For any element which is not adjacent, if you pick any non-adjacent element, we can always prove that there exists some pair. The maximum among these pairs would be less if you are taking adjacent elements. I hope intuitively you would have got what I'm trying to say. So basically the most optimal here is just pick the adjacent elements, first two elements, next two, next two, next two, next two. So just sort the array, pick the two elements, whatever is the maximum difference among these pairings, that would be your answer. Okay, so I hope this logic is clear to you. Okay, so I think we can move to the code part of this. So I take the input, after that I sort the array A, and after sorting I just iterate to every alternate index. So I'm iterating to all the even indices and taking the max of A of I plus 1 minus AI. Okay, so I'm iterating to this, then this, then this, and I take the difference of AI plus 1 minus AI. That would be my difference, AI plus 1 minus AI. And in my answer variable, I just maximize all the possible pairs. That gives us the maximum of the minimum maximum difference in the array. Okay, so I hope if this logic is clear, this sorting would take n log n time, and this loop is taking an order of n time. So we can say that time complexity for this is n log n. Okay, space complexity, the space would be used for the array A, which is order of n. Okay, so I hope this problem is clear to you. We can move to the next problem. Okay, so let's look at problem C. So you are given an array A of length n and a number k, where k is in between 0 to n. In one operation, you can choose any index I and set ai to any integer value x in the range 0 to n. Okay, so what you need to do is, in one operation you can just pick any index and change its value to any value in the range from 0 to. Now you need to find the minimum number of operations required to satisfy the condition that MEX of the array A is k. What is MEX? If you don't know, the minimum excluded of a set of numbers is the smallest non-negative integer x that does not appear in the set. So if you have this array, then the smallest value, smallest non-negative value, that is starting from 0, 0, 1, 2, 3, whichever is the smallest value that doesn't exist in the array, that is called the MEX of the array. Now you want to make sure the MEX becomes k, and the operations available to you is just select any index and replace it with any value that you wish. Now you need to find the minimum number of operations required to make the MEX equal to k. Okay, so let's look at one test case. If let's say you have this is your array A, k is 5. That means you want to make the MEX of array A as 5. What is the MEX currently? You have 0, 0 is not the MEX. You have 1, you have 2, you have 3, you have 4. So 5 is the minimum element which is excluded in this array. So its MEX is already 5, which you wanted to make. So number of operations required here would be 0. So here for this test case, answer was 0. Okay, let's take another test case. So here if you look at this array, then you want to make MEX equal to 2. What is the MEX currently? If you look, 0 is present in the array. Then if you look at 1, that is not present anywhere in the array. So currently the MEX is 1. What you need to do is you need to make the MEX equal to 2. What you can do is, let's suppose you replace this 2 with a 1. Then what is the MEX? You have 0, you have 1, you have 2, 3, 4. MEX becomes 5 now. What you can do is maybe replace this 2 as well with 5, let's say. Then if you look at this array now, you have 0, you have 1, but you don't have any 2. So now the MEX has become 2. So after doing 2 operations, our MEX becomes equal to 2. Minimum operations here was also 2. Okay, that is the minimum requirement. So I hope the problem would be clear what you need to do. Now let's try to think how can we solve the problem. So what you need to do is you need to make the MEX of this array is equal to k. What is MEX? When we can say that the MEX of an array is k? So for MEX of an array to be k, you should have all the numbers from 0, 1, 2, 3 up till k minus 1. All of these numbers should be present in the array and k should be not present in the array. Then only you can make the MEX is equal to k. So these are the two conditions. How can you make all elements from 0 to k minus 1 be present in the array? So you can just look at the array and initially find the frequencies of like all the elements. How many times 0 comes? 1, 2, 3 up till k minus 1. So whichever value would have a frequency of 0, that means we need to have one. Let's say 3 has a frequency of 0. That means 3 is not present in the array. We would have to change some value into 3 in order to make 3 as the in order to make 3 be present in the array. So one operation would be required there. So among 0 to k minus 1, whichever elements among them is not present in the array, 1 plus 1 operation would be required for them definitely in order to convert some other element into that element. And if we check the frequency of k, then let's say the frequency of k is some fk. Let's say frequency is 2. That means we would have to remove all those 2's, remove all those k's, remove the 2 times the k is present in the array. So 2 operations would be required for that. Now here this operation is a removal operation, this operation is an addition operation. So what we can do is, like here if you look at this array, we wanted to make MEX is equal to 2. So for that 0 and 1 should have been present in the array and 2 should have been absent in the array. And if you check the initial array, The frequency of 0 was 1, frequency of 1 was 0, frequency of 2 was 2. So from 0 to 1, this 1 was absent in the array. So we can say 1 plus 1 operation would be required to get 1 in the array. And if you look at 2, the frequency of 2 was 2 in the array. So we can say that 2 operations would be required to remove this 2. But was the answer 3? No, it was 2 only, because what we can do when we are removing a 2, we can remove this 2 and insert a 1 instead. So this is removal operation, this is addition operation. So in one operation we can do both removal and addition. So our final answer we can say is actually the maximum among these two. If there are more removal operations required, that would be our number of operations required. In that only we can manage the addition. If there are more addition operations required, that would be our limit for the minimum that many operations you would have to do. So our answer is the maximum among C0 and C1, where I'm telling C0 is number of elements with frequency 0, number of elements with frequency equal to 0 in the range from 0 to k minus 1, and this is the frequency of k. Okay, so compute the count of both of these and the maximum among them would be your answer. Okay, I hope this logic is clear to you. We can move to the code. So what we are doing here is I take the input array A and I also compute the frequency of all the elements. Now here it was given that AI is from 0 to n only. So I am taking a frequency vector of size n plus 1. Initially frequency of all the indices is 0. What I do is f of AI plus plus. So this way my frequency vector would be updated. For every index, f of I would give me the frequency of I present in the array. Now once I have computed my frequency vector, then I have to compute the C1 and C2. So I had written C0 here, there I'm in the code I have written C1. So C1 is number of elements with frequency 0 in 0 to k minus 1. So I initialize C0 as 0. I iterate from 0 to less than k or 0 to k minus 1. If the frequency of I is 0, I do C1 plus plus. So I get the count of number of elements with frequency 0 in the range from 0 to k minus 1. And C1 is basically the C2 is the frequency of the kth element. F of k would give me that. Final answer is the max of C1 or C2. Okay, so I hope this code and logic is also clear to you. If you analyze the time complexity, calculating this input and frequency is order of n, and this loop is also running n times, so order of n here. Final time complexity is order of n. Space complexity is order of n, an input array and a frequency array. Okay, so I hope this problem is also clear to you. Can we move on to the next problem? Okay, so let's move to problem D. You are given a string S of length n consisting of the characters A and B. Okay, so in one operation you can choose a position I and swap the neighboring characters Si and Si plus 1. You need to perform the minimum number of operations to ensure that all characters of one type, either A or B, are located strictly together, forming exactly one continuous block. So you have a string consisting only of A's and B's. You can perform this swap operation and on any two adjacent elements. And after performing minimum number of operations, you need to make all the characters of any one type located strictly together in continuous block. What does it mean? So here in this you can see all the B's are together. A may be in two separate groups, but all the B's are together. Here you can see all the A's are together. Here all the A's are also together, B's are also together. So that is also fine. You just all these strings are fine. These are valid forms. So you need to convert that string into one such string where either all the A's are together or all the B's are together. Okay, so how do you do that? Okay, let's look at one test case. So here if you look at this test case, now here you can see that B is at different positions, A is at different position, none of them are continuous. How do you make it continuous? So one way to make it continuous would be maybe swap these two positions. So we get a here, a B here. Okay. Maybe swap these two positions. We get a B here, a here. What we have in the string finally is A, B, 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 A, A. So all the B's come together now. After doing this swapping and this swapping, all the B's are together, and in two operations, we have made this string into a valid string. So 2 was the minimum here. You can try different ways, but in one operation, you can never make all of them together. Another way to do it was, let's say we can also do it in two operations like this. We can swap these two to have a B here, a A here, and swap these two to have a A here and B here. What we would get is B, B, A, B. So all the A's become together in just two operations. So there also you require two operations. So 2 is the minimum operations required here. 2 was our answer. Okay, so I hope it is clear what you need to do in the problem. Now let's look at the constraints for the problem. It's n is 2 into 10 to the power 5. So we cannot do something like n square, n cube, or anything like that. We need to do something in order of n or n log n at max. So after looking at that constraints, let's try to think of some logic how we can optimally do this in order of n. Okay, so if you consider any string, consisting of just A's and B's, so what you finally need to achieve is either you have all the B's together and A's in the two sides. Either you need to form this type of string, or you need to form this type of string where you have all the B's, all the A's together and B's in the side. Okay. So here all the B's are together, here all the A's are together. Now it is either of these two kinds that you need to convert. So let's individually check for, if you want to make all the B's together, what is minimum operations required? If you want to make all the A's together, what is minimum operations required? If you individually check both of them, then minimum of both would be your answer. So if you want to check for this, if you want to make all the A's together, now for this also, what there can be different ways, where here you have all the A's here, and here you have, let's say, X number of B's and Y number of remaining B's this side. Maybe you may shift one B that side, and that is your final string. Maybe shift another A, B that side, that is your final string. So when you make a group of A's together, that count of A's is fixed in your string. You are not changing A to B or B to A. So their count remains fixed. You are just swapping the values. So this size of this continuous A's would be same, but there can be different final strings with the number of B's ahead and number of B's behind changing. So if, let's say, you have a string, if you take this string only, here you have 3 A's and 2 B's. So either you can have A here and a B here, B here, or A, B, B. This could have also been your final string, or A here, 2 B's here, 1 B here, or all the 3 B's to one side. All these are your possible different string with all continuous A's. So if you can like fix your final string, then it is like a little bit easy to compute how do you like optimally reach that final string. If you don't know what your final string is, like, it is a bit difficult. So that's why the thinking process is like, think of what final string you are reaching. So these are the different possibilities of the final string that you can reach. Now let's try to think, if you want to reach this final string, what would be the minimum number of operations required? Let's suppose you want to reach this final string. Okay, B, triple A and B. What would be the minimum operations required to reach this final string? So from here we start all the continuous A's. So what we can say is, if you index them, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. So if you look at this starting A, so when you start with this 2, here everything to the left of this should be B. And if you look at this 4, everything to the right of this should be B. Basically, you have to shift all these B's there, all these B's there. Or you can say that from 2 to 4, you have all the A's. So from 2 to 4, all the A's should come. So here, this A is already here, but all the A's to the left of this should come inward and combine here. All the A's to the right of this should come inward and combine here. So we can say that this 3 is like our pivot point, like this index 3 is our pivot point, which would create this final string. That if we do that, from this pivot, all the A's to the left, if you bring them here, and all the A's to the right, if you bring them here, it would create this final string. Or if you, let's say, choose this A as your pivot point, then keep this A here, all the A's to the right, bring them here. That would create a B here and 3 A's here, this final string. And if you take, let's say, this as your pivot point, then make all the A's come this side and B to the that side. This would create this final string. So you can like say that we can one by one, let's say, fix every A as our pivot point and try to, like, whatever A's are to the left, bring them close to this. Whatever A's are to the right, bring them close to this. This thing, like, if this is like a bit clear, that if you like fix one by one all the pivot points, minimum among them, through that you can compute your answer. Now, obviously, going to iterating through every pivot point would again make it something like n square. You have to do it in order of n. So you have to think, how do you optimize it? Okay, but let's once think, if let's say I'm fixing this as my pivot point. Let's say I fix this A as my pivot point. What is the number of operations required to bring all the A's to the left here, all the A's to the right here? So you can say that you would bring this, you would swap like this, you would do one swapping and bring it here. So one swapping was required here. You would do one swapping and bring it here, one swapping was required here. Let's take some other case. Let's say you have B, A, B, B, A, or a B here, A, B, A, something like that. Let's say you fix this as your pivot point. Then you want to bring this and this, both of these A here, and you want to bring all these 3 A's here. So if you look at from the left, then you would have to bring this, swap these two, bring this A here, swap these two, bring this A here, swap these two, bring this A here, swap these two, bring this A here. So in order to move both of them, in order to move this till here, you would require one operation. Move this till here, you would require 1, 2, 3 operations. So 4 operations would be required here. And in this way, if you look, this is already here, this is already here, you can swap this here in one operation. So here you can say number of operations required here was, this should come here, so 3 operations, this should come here, so 1 operation, this should come here, so 1 operation. So 3 plus 1 plus 1, 5 operations would be required if you fix this as your pivot point. Same way, if let's suppose we fix this as our pivot point, let's say, then we would have to bring this A here. So in total 2 is the distance, so 2 swaps would be required. We would have to bring this A here, so 1 swap, bring this A here, so 1 swap, bring this A here, so 1 swap, and bring this A here, so 2 swaps. So in total 2 plus 1 plus 1 plus 1 plus 2. So 3, 7 operations were required for this, which was greater. So now you know, like, if you fix any pivot point, you know how to compute the number of operations. But again, if you fix every pivot point and one by one compute for every A, computing for every A would be order of n, fixing every A would again be order of n. So overall it would go order of n square. You need to compute this optimally in order of n. So what we would do is, if you look from the left, what we are getting is like a prefix type of thing, and from the right is like a suffix type of thing. So you can think of something like a prefix array, suffix array type of thing in order to optimize this. So what I'm saying is, if let's suppose your prefix I represents that if I is fixed as the pivot point, then what is the number of operations required to bring everything to the left here just before I? So what I'm telling is prefix I represents number of operations to bring all, for A if I'm computing, then all A's in the left of I to the positions I minus 1, I minus 2 and so on, depending on the number of A's. So then if let's say for this if I have computed for this pivot point, I had computed this as 7, not 7, before that 2 was required. So prefix of A was in the suffix part, all these were coming, but prefix of this index was just 2, whatever index is that, 0, 1, 2, 3, 4. Prefix of index 4 was 2. Then if you move to the next index, okay, now there may be a B here, but if we have applied the operations to bring all the A's here, that means the string is already A here and B here if we are applied these two operations. Okay, and then if you want to compute for this index, that how many operations are required to bring all the A's just here. So what you would need to do is, whatever there are two A's to the left of this, you would have to bring this A here and this A here. Basically, if there is a B at the ith index, you would have to move this B once, cross this and then cross this. So if there are two A's to the left of this, you would require +2 operations to change the string to B, 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 A, A. So we can say that for this index, prefix 5 is, earlier 2 operations were required, now 2 more operations are required, so total 4 operations are required to bring all of this here. Next, if you move to this 6th index, then in the 6th index we already have a and we have already arranged all the A's to the left here. So whatever was the prefix of 5 would remain the prefix of 6, it would remain 4. So we can say that when we get a, we don't need to do anything, we have already arranged it using the previous prefix. Whenever we get a B, that means that B has to be moved how many times to the left? The number of A's present in the left of this index, that many times it would be moved there. So we can write the transition for this prefix I as, if ith index is B, then we can say that prefix of I would be whatever operations are required to make all the A's come at till I minus 1 plus the count in of A's in the prefix till I, or you can say how many the number of A's that are present to the left of I. So here prefix 5 was 2 plus 2 because 2 was the number of A's present to the left of index 5. Okay, so let's say count A, I denotes the number of A's present to the left of I. So this count can also be, is in itself like a prefix array, it could be computed like a prefix array, and this state can also be updated when si is B and else when si is A, prefix I is just equal to prefix I minus 1. So you can consider this prefix array like a DP, or you can say it a prefix array only. Actually prefix array is a DP only, but okay, so I'm telling it prefix array only. So by computing this prefix array, you can compute for every index I, if you want to bring all the bunch of A's together there, how many operations would be required. Same way you can do for suffix I by iterating from the right side the same thing, that how many operations would be required to bring all the A's to the right of this close to this. So suffix I would be, its transition would be written like suffix I plus 1 plus, depending on whether I is, if si is B, then only you would add the whatever the count of 8 in the suffix of I. Okay, whatever the suffix count of A's. So this way we can compute. Now once this prefix and suffix is computed, you can just iterate to every index. What would be the total number of operations required if this ith index is fixed at pivot, as pivot? The total number of operations required, with I as pivot would be prefix I plus suffix I. Okay. So you can just minimize prefix I plus suffix I over all I once you have pre-computed this prefix and suffix i's. Okay. This thing you can do for A, same thing you can do for B. Okay. This same thing you can do for B. This SI equal to B thing would be reversed. And same way you can compute prefix I suffix I for B and minimize it for B as well. So your final answer would be the minimum of prefix A of I plus prefix suffix A of I. So for array A, the prefix and suffix that you computed, or for array B, the suffix and prefix that you computed. Minimum of this for every index I is your final answer. Okay. I hope this logic is a bit clear to you. The median thing that you are writing, probably that may also work. Like I thought of this approach in the contest, but yeah, if you can prove this, what you have written in the chat, then yeah, that should also work. Okay. So yeah, if this logic is clear to you, we can move to the code. So we'll have to compute prefix A, prefix B, suffix A, suffix B. And in order to compute these prefix, you would have to maintain the count in the prefix, count of A's in the prefix of A and count of A's in the suffix of A. So in total, we would compute 6 arrays: prefix A, prefix B, suffix A, suffix B, and the count of A in the prefix, and or you can say what I've taken in the code is, I'll write that only. Yeah, so the count of A in the prefix and the count of A in the suffix. These 6 arrays, if you maintain, if you want to get the count of B, you can just subtract by the length of string minus count of A would give me the count of B. Okay, so maintaining these 6, pre-computing these 6 vectors, after that we can compute our answer. Okay, so this is the code. I take the string as input, and then prefix A is just I initialize my, first I'm doing computing for the prefix, then I would compute for the suffix. So I initialize my prefix A vector, prefix B vector, and the count in the prefix of A. These 3 vectors. So initially the count for 0 is, if the first character is A, then the count would be 1, otherwise count would be 0. So this boolean would give me a 0 or a 1, that would update my count of 0. Starting from I equal to 1 to n. Now prefix A and prefix B, for 0 it would be 0 only, because if you are at index 0, whether it starts with A or starts with B, if you're writing prefix A of I, that means you want to get everything to the left here only. There is nothing to the left, so no operations would be done. For B also, there is nothing to the left, so no operations would be done. So prefix A and prefix B for 0th index would be 0 only. From index 1, we can compute through our transition. Okay, so prefix, all the 3 I have updated as the I minus 1th index, and then I'll add, depending on the condition. If SI is B, then I'll add count of A to prefix A. So if SI is A, then I update the count of I plus plus. Count of I stores the count of A's till the index I, and for SI is equal to A, I would have to update here prefix B of I would be written as prefix B of I minus 1 plus the count of B's. Okay, so prefix B of I would be how many B are present. If count I is the number of A's, and till index I we have I plus 1 elements, then I plus 1 minus count I would give me the number of B's present before index I. So that much I'll add to prefix of B if A is present here. So just make that A to go, just reach B that many times to the left. That many swapping would be required to shift it left that many times. And in the else case, when SI is B, then prefix A would be updated with the count of A. So prefix A is updated with the count of A. So this way all the prefix arrays are computed. Same thing would be done for suffix arrays. Okay. The suffix n minus 1 is, if the last index is a, then it is a, the count starting from n minus 2 to 0. Suffix I is suffix I plus 1, and the same thing. If it is a, then suffix count plus plus, suffix b plus equal to number of elements in the, if I am at the ith index, number of elements to the right of I is n minus I, minus the suffix count of a would give me the count of b's here, and this is the count of a's here. So this way my suffix arrays are pre-computed. After all these are pre-computed, my final answer is the minimum of answer, or prefix a plus suffix a, or prefix b plus suffix b. Okay, minimum of all these would give me my final answer. Okay, is this logic clear to you? Just use prefix to get suffix. Like for count you can use, like for this count you can use prefix to get the suffix count, but for these prefix and suffix arrays that I'm defining that if this is taken as pivot, then how many operations would require to shift all this in the left here, and suffix I represents how many operations would be required to shift everything from the right here. So both of these are different. From prefix I you cannot compute suffix I, because in prefix I am considering operations from the left, in suffix I am considering operations from the right. So that's why they are different. You cannot do anything using prefix I, you cannot compute this. This is not a prefix sum array. Okay, so I guess any more doubts in this? Okay. Yeah, some of you are writing that it's optimal to choose the median elements. Yeah, it can be proved, and that thing also. So if you want, then yeah, that logic is also fine. That if you have some A's at some of these positions, these are some random positions, there may be some B's in between. Then whatever is the like median of that, if you take that as the pivot element, that would be the most optimal. Because you have to shift all these here and all these here. If you take anything to the right, then some shifting more elements from the right and less from the left would mean like more operations. So it would be always optimal to, whatever is the median element, either pick this or this as your pivot element and then apply the operations. That would be most optimal. So yeah, that logic would also be fine. Then you would not need to compute the prefix and suffix arrays. Okay. So yeah, so I guess we can move to the next problem now, or any other doubts? Okay, so let's move to problem E. In the world of deep Woken, there exists an ancient artifact, this on which a sequence of n mysterious symbols is engraved. It is said that the true power of the artifact can only be revealed by finding all sacred fragments, continuous segments of the tablet that contain exactly k distinct numbers, and their length must be between L and R inclusive. Okay. Given a sequence A of length n and integers k, L, and R, you need to find the number of such boundaries B and C such that B and C are in the range from 1 to n. Among the elements from AB to AC, there are exactly k distinct elements, and the size of the range is in between L and R. So satisfying these conditions, you just need to find how many such ranges from B to C exist, so that the number of distinct elements in that range is k, and the length of that range is in between L to R. Okay, so you are given an array A along with k, L, and R, the three fixed parameters, and constraints are up till again 2e5, so you need to do something in order of n only. Okay, let's look at one test case. So if you look at this test case, you are given an array A along with k, L, and R. Okay, so you need to find in this array A how many some such ranges from A to B exist, so that let's say you take the range from 2 to 3. Okay, that means this range from 2 to 3, so that the number of distinct elements in this range is equal to k exactly. So here number of distinct elements is 1 and 2, so two distinct elements, which is equal to k, so that is fine. And second condition is the length of this range, so the length of this range is 2, that should be in between L to R. So the length of this range should also be in between L to R, and the number of distinct elements should be exactly k. How many such ranges exist? So this was fine, the length was 2, which was in the range from 2 to 3. So this is one such good range. How many such exist? Maybe if you look at this particular range, okay, so 2 to 3 is fine. If you look at 1 to 3 here, then number of distinct elements again here is 1 and 2, so two distinct elements, which is fine. Length of the range is 3, which is also fine. So this is also fine. If you take something like, let's say from 1 to 4, again here the number of distinct elements is 1 2 3, so three distinct elements, it doesn't satisfy the condition, this is not valid. Okay, if you take something like 1 to 3, then the length of this range is 2 and there are two distinct elements, so 3 4, 3 to 4, this range is also fine to go. So likewise there would be many such valid ranges. You need to print the count of such valid ranges. Here it was 5, so there were in total 5 such valid ranges. 3 to 4 was there. Then you may look at this range, this was also fine, and maybe you can look at which other would be there. So this is basically 4 to 5, this is 4 to 5, this was fine. And what is the fifth one? 1 to 2. This range is also fine, this we have not mentioned. So two distinct elements and length 2, so 1 to 2, this is also fine. So for this test case, these 5 were the valid ranges. Other than that, for all the ranges, it doesn't satisfy both of the conditions together. So 5 such ranges satisfy it, so our answer was 5. Okay, so if this thing is clear, how do you solve the problem now? So one thing is, if you like iterate through every L and R and check for every range, then while iterating you can maintain the frequency of the elements in the middle, or the distinct elements. Using frequency you can maintain the distinct elements, so the count of distinct elements can be maintained and the size of the range can be checked, so you can do all the checkings. So checking for all the ranges, okay, can be done in order of going through all the ranges is n square, and log n maybe to updating thing. But n square log n is still not fine because n is given as 2e5. Okay, so you need to optimize it to maybe n log n type of thing. Okay, n square is not fine, you cannot check all the ranges. So how do you optimize it? Okay, if you are checking only for ranges of size from L to R, again this L to R may vary as L equal to 1 and R equal to 1. Basically then you would need to check for all the ranges, again it would go n square. So how do you optimally check it? Okay, now think of this problem like let's take this array. Okay, let's take this array. Here the test case was this. Okay, so K, L and R were this. Okay, so what you need to maintain is, in a range there should be exactly K number of distinct elements. So let's try to whatever now when we were checking for all possible A and B, then there were n square number of ranges. Let's fix our right end of our range. Okay, let's say we fix this as our right end, this as our B. Okay, now if this is the right end, then if we can optimally try to count how many such such left ends exist which are valid, then we can just sum up for all the right ends. Okay, so if you fix the right end, if this is taken as A, then how many distinct elements would be there? So first of all, first thing you need to make sure is there are just exactly K distinct elements. Then we would check whether that size of range is in between L and R. Those things we would say. First, let's try to check how many distinct elements exist. So here, if you take this full range, number of distinct elements is 1, 2, 3, 3. If you take this range, again, removing 1 doesn't change it, it still remains 3. If you check this range, this still remains 3. If you check this range, it would reduce to 2. If you check this range, it would reduce to 1. So if you look here, then from this, all these three ranges, number of distinct elements was 3. So all these 3A are your possible A's. And then among them, whichever would have a length from 2 to 4, you can take the intersection of the sizes with 2 to 4 and get that length. That is fine. But if you can compute this 3 fast, like how you can get, like you can just, you are iterating through B and you can just very fast, if you can get that from some point I till some point J, if you vary your A, then it would still have K number of elements, distinct elements only. Okay. If let's say K was 2 here, then for all these ranges, our answer was 3. Or then if you reduce this to this range, our answer was 2. And here our answer became 1. So the range where we get 2 as our answer is just this A. Only one A is possible for which we get 2 as our answer. So if you are fixing the right range, then initially you would get the maximum number of distinct elements, then either it would remain same or it would reduce, then remain same or it would reduce. So it would be always decreasing the number of distinct elements which you can say. So how can you find that when it is exactly K? And so if you like try to find that what is like the maximum J for which this range has exactly K elements, and the maximum maybe I for which this range has K plus 1 elements, then from I plus 1 to J we would have K elements. This you can understand that for an array A, if let's say I fix this as my B, okay, what different A's can I take? Let's say for this whole range, maybe I was getting some, X number of distinct elements. Here I was still getting maybe X only, and then X minus 1, X minus 1, X minus 2, likewise. It would keep on decreasing as we move our A forward. The number of distinct elements would keep on decreasing. You need to find that what is such a point, so that such a point, let's say J, so that here the number of distinct elements is K, and such a point I, so that here the number of distinct elements is K plus 1. The largest such J and largest such I, if you can compute that border, then I can say from I plus 1 to J, if you keep your A anything in the range from I plus 1 to J, in this whole range we would always get K as the number of distinct elements. So when, if you look at, if you are moving your A forward, can you think when does the number of distinct elements decreases? Here we had K plus 1 and here at I plus 1 we have K only. What would be that point I to I plus 1? It would be a point so that the ith element is such an element so that it doesn't occur anywhere here. So if we were including this whole range, then let's say the AI, we have a X here. Then in this whole range, there was a X present, but in this whole range, since the number of distinct elements reduced, that means X is not present anywhere in this range. X was just present once in this range here, and then we removed it. So one less element is present as the number of distinct elements. So what is such kind of position? This we can say is the last position of X. Okay. So in the prefix, whatever elements if we are getting, if we can store the position of every ith elements, the list of positions of the ith every element, then whatever is the last position of X, of every element X, so whatever is the last position of X, that would be such a position where if you move forward, the number of distinct elements would reduce. Or we can say that if you have stored the positions of all the elements in this prefix, if you have just stored the last position, even this whole list is not required, just store the last position of x, last position where x occurred in this prefix, then we can say that among all the different x, all the distinct elements that are present in this prefix, if you store the corresponding last positions, then whatever element is here, its last position would be here. Whatever element is here, if they are same, then its last position would be here. If they are different, that would be some other element. So we can say that if you move from this side, you get one element here, then if they are same, it would remain one. But if this is the last position of some other element, it would increase, increase, increase. So until we get k last positions. So in the list of last positions, let's say this is one of the last element of some element, last position of some element. This is last position of some element. This is last position. This is last, something like that. So if you take your A somewhere here where we have only one last position, that means one distinct element occur here. If you take this as your A, that means two distinct elements occur here. If you take this as your A, three distinct elements occur here. So while moving forward, we can just insert the position of this and update our last position in a map. Let's say this last position X, this is a map. We can update the last position of X whenever we move to some new index, whatever value is there. We can say that the last position of X is updated to I. So this last position would be updated, and maybe in a multi-set or a set, we can store these current last positions. So whatever the previous last position of this X was, remove it from the multi-set and insert this current last position here. So in that multi-set, if you take the highest k elements, that multi-set would be sorted in the order of the positions. If you take the kth position in that multi-set and k plus 1th position in that multi-set, their difference would give me the range of A. Basically, you can get the range of A from the kth and k plus 1th element in the multi-set. So what I would do is I would only maintain that multi-set or the set, whatever you say. I would only maintain the set till size k plus 1. In order to do it optimally, I would maintain a set of size k plus 1. If there is something which comes after k plus 1, it would not be added to the set. If it is in the first k plus 1 elements, it would be added. Then we can look at the last position of the set, the k plus 1th element, and the last second position, which would be the kth element. This would give me the range of my A, what we can pick. And depending on that range, if this is your range, you get the range of sizes that you get. You can take the intersection of that size with your L and R and get how many valid A exist for this fixed B. So this thing you can, while updating this map and this set in log n time, in log n time only you can update for the next B how many valid A exist. In log n time you can compute. So overall in n log n time you can compute. Okay, I'll just show a quick dry run to see how the algorithm is working. Let's look at this array only. Okay, so if you look at this, so I'll start from the first. Then in a map, let's say last position map. Okay, initially the last position map doesn't have anything. That means nothing has occurred as of now. When we move to this one, we would update in this map. In the last position map, we would update that one, the last position of one is, I'm taking 0 based indexing here, is 0. Okay. Then once this is updated and I have the set st in which I'm insert a pair of last position and the element. So once this is inserted, I'll insert 0 is the last position and 1 is the actual element, so that the set is sorted based on the last positions. We want the set to be sorted based on last position. So here k was 3 and L and R were 2 to 4. L was 2 and R was 4. Okay, so this is my set currently. Okay, then first I'll check if the size of the set, okay, in my set currently I have only one element. So if the size of the set is less than k, that means currently we cannot form any valid set. At least the size should become k first, then only we can have k distinct elements. So we'll move forward. We'll move to this 2 now. Okay. Now we get a 2. So in our last position, we'll update the last position of 2 is this index 1. Okay, and we'll insert this in our set as well. So in our set, we would have at last position 1, we have a 2. Okay. Then we move again. The size of the set is still 2, which is less than 3. So we move forward. No valid things are possible. We move to the next. We have a 1, which is already present in our map. So we'll update its last position from 0 to 2. Okay. Now when this is updated in this set, we will remove this and we will remove this and insert this. So we'll remove and insert 2 comma 1 now. Okay. So because that earlier last position is now invalid, the last position of 1 has changed, so that would have to be erased from the set, and the new last, according to the new last position, the new pair would be inserted in the set. Now again, still the size of the set is just 2, which is less than k, so we move forward. Now we get a 2. If you get a 2, you would update this last position into 3, and once this is updated, we'll remove this and write 3 comma 2 here. Okay, again size of the set is 2, we move forward. Now we get a 3, which was not present in our map, so we write the last position of 3 as 4. Okay, so our map got updated and this would get inserted in our set. So 4 is the last position of 3 that got inserted in our set. Okay, now if you look, the size of the set has become 3. Okay, which is equal to k. That means we can get one valid answer. Now since the size is equal to k, it is not greater than k. Okay, that means whatever we can just take from the starting only. Okay, basically if it would have been k plus 1, then we would have to search that till here we get k and till here we get k plus 1, then in between we are getting or k and k minus 1, to be precise, k and k minus 1, you would have to check that till here we get k, till here we get k minus 1, then in between we are getting. So here you would check whatever is the last position of k. So here if you are here, then you can have this, all these as your answer. So in this last position array, whatever, since its size is k, whatever is the first position, which is index 2. So if you keep your a till this index 2, anything behind this, all of them, anything behind this 2, all of them would give you a number of distinct elements as 3. That means you can keep your a here, you can keep your a here, you can keep your a here. So there are these 3 possibilities for your a. For this you get a length of 3, for this you get a length of 4, for this you get a length of 5. That means we can have lengths from 3 to 5. That means we can have valid lengths from 3 to 5. And our valid range of length was from 2 to 4. So if we take the intersection with 2 to 4, if you take their intersection, you get 3 to 4. So that means 3 to 4 has a size of 2. That means only 2 valid ranges are there. So among them, 3 was valid, 4 was valid, but 5 was not valid. It goes out of bound. So if you take the intersection of these two, you get 3 to 4. So in your answer, you would add a plus 2. Okay. So here you add a, in your answer, you update from 0 to 2. Okay. You update your answer. Then you move forward. Then you would move forward. You move to a 5. You update the index value for 2 as 5. Okay. Let's say here instead of 5, to understand better, let's say we had a 4 here. Okay. Till here you would have got, so let's say I change this value to 4. If we had a 4, then we would insert a 4 here, insert its position as 5. Okay. This our last position map would be updated, and here we would insert at position 5, we have a 4 in the set. Now the size of the set has become k plus 1. So once the size of the set has become k plus 1, the first element of the set denotes that before 2, if you take anything, we would have k plus 1 distinct elements. And the next element in the set 3 represents that from index 3, you would have k distinct elements. So from index 3 and beyond 2 you would have k plus 1. So in this range you would have k plus 1, and here from 3 you would have k. So you can write this minus this range. Only one valid a is possible here. Only one valid a is possible here. So we can say that this is the valid a possible here, and its size is 2, which is in the range. So we do plus 1 to our answer, make it 3. Likewise you have to move. Okay, so when there are, now whenever the number of elements would exceed k plus 1, we would just remove the first element from the set to maintain the size of the set as k plus 1, because we would never require more than k plus 1 elements. Okay, so we'll always remove the, if the size of the set becomes more than k plus 1, we'll remove the first element from the set, the oldest element, and if it is equal to k, then find the first element would be the last value, which gives us a size number of distinct element as k. And if there are k plus 1 elements in the set, first gives us for k plus 1, second gives us for k. So their difference would give me the valid a's. Okay, so I hope if this dry run is also clear, we can move to the code. So yeah, so first we take the input and then I maintain a map. This is the last last index map. Okay, the last occurrence map that I was talking about, last position of I. This is stored in my map MP, and my set stores a pair, this pair that I was talking about in my dry run. Okay, now initially both of them are empty. I start with answer equal to 0. I iterate through every element. If x is my next element, and I check if x is not present in the map, or if x is already present in the map, then I'll erase its previous value from the set. I'll insert, make the last position of x as I. I'll update the map. I'll insert the new mpx comma x into the set. Okay, so this way we are inserting, and if it was already present, we are erasing that from the set. So once this is done, we have updated our map and the set. Now I'll check if the size of the set is greater than k plus 1. I'll erase the beginning of the set. So if the size exceeds k plus 1, then the size could go up till n. So if we are not erasing it, then in order to find the kth and k plus 1th element from the end, it would take an order of k time. But if we are maintaining only a set of size k plus 1 only, then we can just search for the first element of the set in order of log n time only. So since we are not required to have more than k elements, so we are only maintaining k elements. And now if the size of the set is less than k, we put continue, nothing would be added to the answer. Now only possibilities are if the size of the set is k or the size of the set is k plus 1. So in if part, we write if the size of the set is k, that means k dot begin first gives us the last position, as had happened in this case. It gives us the last position, which is a valid a. So starting from 0 up till this position, all of the a's would be valid. So low stores the smallest range. So with this as the last position, this would be the smallest range. So current I minus this st dot begin plus 1. This would be the size of the smallest range, and 0 is the leftmost highest size of the range. So highest size of the range is just I plus 1. Take the full prefix. And if the size of the range is more than k, which is k plus 1, then I take the first element of the set represents for k plus 1. So first element of the set represents for k plus 1. So from I, if we remove k plus 1, this would give us the highest size of the set. So high would be I minus st dot begin, and the next of st dot begin, which is the second element in the set, corresponds to the last index where the size, the number of distinct elements is k. So for k, we get the lower range of the valid size of valid ranges, and we take the intersection of low comma high with L comma R. So low max of low comma L, high max min of high comma R. This way, in low high, we would take the intersection with L comma R, and if low is less than equal to high, we add the size of that to our answer. Okay, I hope this thing is clear to you. Okay, so is there any doubts in this? If you analyze the time complexity, input part takes us order of n time. This inside the loop, we are doing this in erase from the set, which would take log n time. This insertion into the map, updation in the map takes log n time. Insertion in the set takes log n time. Erase from the beginning would take order of one time only, and st dot begin next would take order of one time only. These are all order of one. So overall, we can say n times we are doing log n operations. So n log n is the time complexity in the worst case. Okay, and space complexity, if you talk about, we are just using a map which would have a highest size of n, set would have the highest size of n, input array would have a highest size of n. So order of n. Is this clear? Okay, so let's move to the next problem, which is problem F. Okay, so Nezuko suddenly woke up on the number line at point 0 and has H health points. She wants to reach point D. In one turn, she can do exactly one of two things: rest in the shade and increase her current health by 1, move from her current position X to X plus 1. Okay, each movement decreases Nezuko's health in the movement. If the movement is the jth consecutive movement, her health will decrease by J point. If as a result of a move, Nezuko's health drops to 0 or below, she cannot make that move. Okay, so basically, if she is moving continuously, the decrement in the health would increase. So let's say if she starts from 0 and moves to 1, first decrement is decrement by 1, her health decreases by 1. Then again, if he continuously takes the next move, then the health would decrease by 2. Again, he takes the next move, health would decrease by 3. Now if she rests and restores one health point, her health would increase by 1, and then if he takes the next move, it would again reset and start in the decrement of health would start from 1 again. So the decrement of health would be the number of continuous movements of type 1 she has done continuously currently. Once she takes a rest, that would just reset and start from 1 again if she takes another movement. Okay, so find the minimum number of turns required for her to reach point D. Now you need to find minimum number of turns required to reach point D. So resting and taking the save would count as 1 turn, and moving to the next position also counts as 1 turn. So you need to minimize the total number of turns that she takes in order to reach the point D. Okay. H and D are given up till 10 to the power 9. So even something like order of H or order of D won't be accepted. You have to do something in order of 1, order of log H, log D, something like that. Okay, so let's take one test case. So let's say you are given first test case H equal to 3 and D is equal to 2. So if she initially has 3 health and she wants to move 2 steps forward, she is at 0, she can move to point 1 by doing a -1 in her health. Okay, and then if she want to move to point 2 next, it would do a -2 to her health and her health would become 0, so she cannot perform that move. So next she would rest. Okay, so first she would move to 2, next she would definitely have to take a rest, so she takes a rest and her health increases by 1, becomes 3. Next movement she moves and her health reduces to 2, but she has reached point number 2. So in 3 moves she is able to reach point number 2. So for this test case our answer was 3. Okay, so I hope it would have been clear like what we need to do in the problem. You start with some point 0. If you keep moving, -1, -2, -3, that wise it would reduce. If you take a rest, and then if you move, then again it would reset from -1, and this rest would add up +1 to the health. At any point of time, her health should not become 0 or less. Okay, if her health becomes less than 0, that is an invalid move. Her health should remain greater than 0 throughout the movement, as she need to reach point D in minimum number of operations or minimum number of movements plus a health recovery time that she takes. Okay, so how do you optimally solve this problem? Okay, now let's try to think what would be the, if you are trying to minimize the number of turns, so how many turns would be of type 1 and type 2? So type 1 is recover health, like take shade and recover health, and type 2 is move. Okay, so if I'm telling that I want to reach from point 0 to point D, how many type 2 operations would be required? So we have to do a total of D movements. So this number of type 2 operations would be exactly D. This is for sure. Once we are able to perform D number of type 2 operations, we are done. But in order to do these D number of type 2 operations, if our health is not sufficient initially, then it would like decrease very rapidly if you are just doing this continuously, -1, -2, -3, -4 likewise. So if you are not able to do it in just type 2 operations, you would have to take the help of type 1 operation. So you just need to minimize this number of type 1 operations. This is your variable thing that you need to minimize. Okay, let's say we fix that we are doing X number of type 1 operations. So you can see that you can easily apply a binary search here, that if I'm saying that I can do it in X number of type 1 operations, or if I'm telling that my answer is X, that means number of type 1 operations would be X minus D. Okay, let's say this is Y. Okay, so total number of operations is D plus Y. Okay, so if I'm telling my answer is X, the number of type 1 operations is X minus D. So basically this D is fixed and this number of type 1 operations is variable. So if we can do in Y number of operations, then we can obviously do in Y plus 1 operations as well. So this is a predicate function. You can easily recognize this, that if you are taking one extra rest, this would never be any harm to you. So you can just add one extra rest. So we can say that if we are doing a binary search on answer, then up till some X, it would be not possible, 0 0 0 0, not possible to do it to minimize our answer to this X, and from some X plus 1, we would say that now it is possible. So if it is possible for some X plus 1, it would be possible for X plus 2, X plus 3, X plus 4, and so on also. So this X plus 1 is our minimum. So we have a predicate function, so we can do binary search on answer. The only problem is how do we write the check function. So I'm telling that X is the number of operations, total number of operations that we are doing. Can we reach D? So our check function would be, check of X would be, can we reach D with X operations? This is our check function. Now, how do you check that? So if you think what is like most optimal, now you have X, so let's say Y is X minus D. So basically you can say Y is the number of type 1 operations that you are doing. Okay, so if Y is the number of type 1 operations you are doing, where would you place those type 1 operations so that you can optimally basically get to the point D with minimum number of health reductions? Okay, so if you look at the series, let's say you perform some type 2 type 2 type 2 operations, then you perform a type 1 operation, then some type 2 operations, then some type 1 type 2. Okay, whatever series you have, if you have something like this, what would happen? For the first type 2 operation, you get a -1 to the health, next -2, next -3, next -2. Whenever you get a type 1 operation, you get a +1 to the health, and then again it would reset and start with -1, -2, -3. If you get a 1, you get a +1, +1, and again you start with -1, -2, and so on. So if you divide, you just need to find some order of operations that you would perform, where you perform D number of type 2 operations and Y number of type 1 operations. What order should you choose so that it never happens that your health reduces to less than 0? So we can see that how many at the end, how many health reductions do we get in this particular order. So for a range of 2s, you would get -1, -2, -3, -4. So this is basically sum of all numbers from 1 to 4. So 1 + 2 + 3 + 4 minus that much you would get in your health. Whenever you this 1 divides it into groups, then you again have a group of this. So again here you would get -1, -2, -3. So basically this is sum from 3 to 1 minus of that. Then in this group again, if you have x number of 2s, it would be x into x plus 1 by 2. That is the sum from 1 to x minus that much. And in plus, how many you would have? For every type 1 operation, you get a +1. So you would have plus y health. So this minus of this plus of this, if you can like maximize this overall thing, basically minimize these minus things, then at the end, if this overall thing plus the initial h health that you have, if this overall thing is greater than 0, we can conclude that we can reach the end. One case here is, what if at the middle only, if at the end we have greater than 0 health, but in the middle we have less than 0 health. Okay, so let's for once ignore that. We'll look at that, but let's see if you want to just minimize your end health. Okay, maximize your end health, minimize the reductions in your health. Then what is the most optimal way to place these ones? If you look here, let's say your D is 8 and your Y that you are checking for is 3. Then either you can have type 2, type 2, type 2 operation, a type 1 operation, type 2, type 1, type 2, type 2, type 2, 1, 2, 3, 4, 5, 6, 7, 8. Or a type 1 and then type 2. Okay, let's say you have something like this. So here you would have 3 into 4 by 2. You would have 2 into 3 by 2. Sorry, 1. Basically, you have a group of 3, a group of 1, a group of 3, a group of 1. So using 3 ones, you have divided it into 4 groups. Is this like optimal? Because ones would give me +3, but we want to reduce these. So with this, for a 3 you would get -1, -2, -3. For a 1 you get -1. For a 3 you get -1, -2, -3. For a 1 you get -1. If you want to reduce this, so if you change this 1 here and 2 here, so basically you shift 1 from 3 to 1, it would change to 2 and 2. 2 and 2 would means -1, -2, -1, -2. That means you had -1, -2, -3. So -1, -1 are still there. And instead of 1 -3, when you shifted it here, it became -2. So it was more optimal to shift it here. Again, this one can be shifted here. So this 3 can be reduced to 2, 2. That would be most optimal. So the most optimal way to divide them is, because the greater size of range you have, the decrement value increases more. So if all these ranges are of equal size, that would be most optimal. You can get it. Okay. So basically, we have to place these ones so that I divide these group of D2s that I have, D times the second operation that I'm performing. I have to divide it into, if I have Y number of ones, then Y plus 1 number of groups. So divide D into Y plus 1 groups of equal size. Now, it may happen that D is not divisible by Y plus 1. Then in that case, it would not be possible to divide all of them in equal size. Then still what you would try to make them almost equal in order to make it optimal. So let's say you have d is equal to 11 and y is equal to 3, let's say. So y plus 1 is 4. Y plus 1 is 4. That means you have to divide 11 into 4 groups. Now since 11 by 4 is not divisible, what you can do is seal of 11 by 4 is 3, and the floor of 11 by 4 is 2. So basically divide them into groups of 2s and 3s. So you want to have 4 groups of 2s and 3s. So you would have 3 plus 3 plus 3 plus 2. You can have something like that to divide all of them equally. Okay. If it would have been 10, then 3 plus 3 plus 2 plus 2. So how many 3s do we have? It's 11 modulo 4 is 3. So whatever is d modulo y plus 1, that many times you would have d upon y plus 1 seal, and whatever is the remaining for you can say y plus 1 minus, you have to divide it into y plus 1 groups. Out of them these many groups are done, so y plus 1 minus this gives us the remaining number of groups. The remaining number of groups would have the floor of this. So these many groups have so you have these many groups of this size and these many groups of this size. So for a group of size something, let's say this size is some z, let's say if the size is z or sz is the size, for a group of size sz, how many health loss it would produce? It would produce a health loss of size into size plus 1 by 2. So the total health loss we can say is size into size plus 1 by 2 multiplied by the number of groups, and same way for this size into size plus 1 by 2 into the number of groups. So this way, for the most optimal case, we can get that how many reductions we have. In that, if you add the number of type 1 operations, which would be y, and the health h, then if that overall thing is greater than 0, we can say that the check function will return a yes, it is possible to do. If that is less than equal to 0, it will return a no, it is not possible. Now, one thing that we need to still consider here is, what if we are only counting that at the end I'm just checking whether the health is still greater than 0 or not. What if somewhere in the middle the health reduces to less than 0 and then it increases and comes to greater than 0 at the end? Is it possible? Can that happen? What I'm telling is, first of all, what would be the upper bound on my range in the binary search, upper bound on my answer? At max, like how many operations would be required? So like minimum number of operations required would be d, y equal to 0. So if like in d operations only, you can just in one group only do all the operations, you have enough h health at the start, that is fine. So d is the value of my low in my binary search. D is the minimum answer, and my answer cannot be less than d. What would be the high of my binary search, the upper bound on my range of answer? If we do, let's say 2d times, if we are checking whether we can do it in 2d number of operations. 2d operations means d operations of type 2 and d operations of type 1. If we take d operations of type 1, can we say that we can always do it like just divide it into groups of ones? So when we have just groups of ones, just do 2 1 2 1 2 1 2 1. Initially your h is given as greater than equal to 1. So first operation you can do, or start with 1. Let's say you rest, then do second operation, rest, then do second operation, rest, then do second operation. So in this way, if you do d number of first operations, then initially your health is greater than equal to 1. With one rest, health becomes greater than equal to 2. Health reduces by 1. Then a plus 1 minus 1, plus 1 minus 1, plus 1 minus 1. Health would never reduce to less than 1 if you do it something like that. So we can say that at max my answer can be 2D. If I'm telling my answer is greater than 2D, that in 2D we can always do it. We don't need to check for answers greater than 2D. So at max my answer can be 2D. So in my binary search, we only need to check in between D and 2D if I can reduce my answer from 2D. Now, if my answer is less than 2D, that means my Y is less than D. Okay, number of type 1 operations are less than D. If number of type 1 operations are less than D, then this ceil value that I'm getting, D upon Y plus 1, this would be greater than equal to 1. This would be greater than equal to 1 for sure, since this denominator Y plus 1, if D is less than Y is less than D, at minimum it is 1. So that means the size of every group is at least 1. If the size of every group is at least 1, then in any combination, if I'm telling that at some particular point my answer reduces to 0, then after that we have greater than equal to 1 as the size of every range, which would do at least a -1, and with a single one you get a +1. So the totals, if it has already reduced to less than 0, and for it to become greater than 0 after that is not possible, because we have more negatives than positives, or at least equal number of negatives and positives after that. So if we are checking that at the end the sum is greater than 0, then in between also the sum is decreasing only, it is never increasing. So if at the end the sum is greater than 0, then in the middle also the sum would remain greater than 0. So this way we can prove that if you do these optimal partitions and compute your answer, that this with this as size, these number of minus operations multiplied by this, with this as size, these number of -1 operations multiplied by this, the total number of reductions in health you get by dividing it into equal groups, plus the increase in health plus initial health, if that thing is greater than 0, then we can do in that X number of operations. That would be the check function for my binary search. And with that as the check function, we can easily compute our answer. All these computation, mod and division, all of these would be done in O of 1, and binary search would take a O of log n time. So overall in order of log n time, our answer is computed. Is this logic clear to you? Is there any doubts in this? Okay, so let's look at the code for this problem. So I apply the binary search on answer. My low is set to D, high is set to 2D minus 1. If none of from D to 2D minus 1 satisfies the answer, then 2D would definitely satisfy our answer. So I initialize my answer with 2D and I'm checking from D to 2D minus 1. I'm trying to get the maximum possible answer. Now I take the mid. Now this is like my check function where I'm checking whether with mid as the number of operations applied, with can mid be my answer? Can I do all the reach the point D with mid as the number of operations? So I check the number of groups. This Y plus 1 is the X here in my code. Mid minus D is my Y, plus 1 is my Y plus 1. So X in my code is actually Y plus 1. Okay. Now S1 is the first size. This first size is D upon Y plus 1, the ceil. Okay. Or the first term, D upon Y plus 1, the ceil, multiplied by this. So D upon X. Okay. If you are doing an integer division, it would be floor. Okay. This is the S1. The floor division. Yeah. So this floor division thing is taken as S1. So this into this plus 1 by 2, size into size plus 1 by 2. So d by x into d by x plus 1 by 2 gives me the S1, and S2 is whatever was the floor plus 1 we are taking. Like when it is exactly divisible, d modulo y plus 1 would become 0. So basically it would not be present anytime. So we can take for it would be only present when d is not divisible by y plus 1. So when d is not divisible by y plus 1, the ceil of d by y plus 1 is basically the floor plus 1. Okay, so the floor of d by x plus 1 is basically the ceil, and that, so d by x plus 1 into d by x plus 2 by 2 gives us our s2. So we can say that d modulo x into s2, d modulo x into s2 plus x minus d modulo x minus d modulo x multiplied by s1. This is our total s. If that total s is less than h plus mid minus d, which is h plus y, okay, h plus y is the total health increments that we get, s is the total health decrements that we get. Then if total increments is greater than the decrements, then our check function is satisfied. Mid can be our answer. I do high equal to mid minus 1 to check even can we reduce the answer more to minimize our answer. Else low equal to mid plus 1, search for a better answer. Okay, and we print our answer. Okay, so this is how we compute all these operations inside our order of 1, and this binary search would take a log n time. So we can say our time complexity is order of log n, and not log n, log d, we can say d. Okay, so the range of binary search is from d to 2d. So time complexity is order of log d, and space complexity is, I guess we are just using normal variables, no vectors, so order of 1 constant space is used here. Okay, I hope this problem is clear to you. Is there any doubts in this, or should we move to the last problem? Okay, so I guess we can move to the last problem. Okay, so let's look at the last problem, which is problem G. So in the Ruthless book and all, let's ignore the story. This is the problem basically. You are given an array of n integers called performance records in Q queries. Each query specifies a subarray from L to R. In this subarray, find all record values that occur strictly more than R minus L plus 1 by 3 times the floor of this. So basically you are given an array of size n and you have Q queries. In every query you need to find, you are given L to R, that whether in the subarray from L to R, you need to find all those records which occur more than R minus L plus 1 is the size of the subarray. Size of the subarray by 3, whatever is the floor of this, strictly more than that. So what all values occur more than 1/3 the size of the array, which have a frequency of more than 1/3 the size of the array, you need to find those values, print those values. So if you see, let's look at 1 1 2 3, let's look at this second test case only. So basically here you were given this array A, okay, and two queries. First query is from 1 to 4. So first query is this whole subarray. Subarray 1 2 1 1 2 3, the whole array. For this whole array, the size of this array is 4. So the ceil of 4 by 3, the floor of 4 by 3 is 1. So the elements whose frequency is strictly greater than 1. That means the frequency should be at least 1 plus 1, we can say 2. So elements whose frequency is greater than equal to 2, we need to find that. So 1 has a frequency of 2, 2 has a frequency of 1, 3 has a frequency of 1. So there is only 1 which has a frequency strictly greater than 1. So its answer is 1. But 2 to 3, we can say we have a subarray 2 comma 3. Here the size of the subarray is 2 and 2 is the size. So 2 divided by 3 floor is 0. So we can say all those elements having frequency greater than equal to 1 are valid. So 2 has a frequency of 1, 3 has a frequency of 1. So answer here would be 2 and 3 both. Okay. So first test case answer was 1 second. This is the test case. 5 was answer for first, and 2 to 3. Okay, 2 to 3 was this range, not 2 to 3 was this subarray. So same, the thing would remain the same. In this subarray, we have 2 comma 1 comma 2. We had 1 comma 2. Size was 2. All those elements having frequency greater than equal to 1. So 1 and 2 have frequencies greater than equal to 1. So our answer was 1 and 2. Okay. So I hope this is fine. 1 and 2. So I hope you would have got what you need to do. That you are given an array, and in every query you are given L to R. For the subarray from L to R, how many elements in this subarray occur having frequency greater than the size of the range by 3 floor, having frequency strictly greater than 1/3 the size of the array. Okay, so how do you solve this optimally? If you like do the brute force, then for every query, if you are iterating through the whole subarray and finding the frequencies, that would take an order of n time for every query. N into q would give you a TLE, because n and q are till 2 into 10 to the power 5. So how do you do this optimally? So the approach that I'm going to discuss is, we can do this, perform these queries using a segment tree. So we have, so what we have here is, for every query you have this array A. So in this array A, you want to compute from L to R. In this subarray, what is my answer? So answer for this subarray is, how many elements have frequency greater than 1/3 the size. So like first thing to observe here is, what can be the maximum answer to any query, maximum size of my answers to any query. Basically, how many such values can exist in a subarray having frequency more than 1/3 the size of the subarray. So here for this, some queries we may have answer of size 1, size 2, size 1, 2, maybe somewhere we would have -1, which would be which is what we need to print if none of the values satisfy the condition that frequency is greater than 1/3, then we would print -1. So basically that would be a size of 0. So in any valid range from L to R, how many valid answers can occur at max? So if you try to think, then according to the condition, if the size of the subarray is, let's say, 8, then 8 by 3 is, flow division is 2. So all those elements having frequency greater than equal to 3. So in an array of size 8, if 2 elements have a frequency of 3 and 3, then no other elements can have frequency more than 3. If the size was divisible by 3, if the size was equal to 9, then 9 by 3 was 3. So again, now our threshold becomes 3 plus 1, 4. So greater than equal to 4 becomes our threshold. So if 2 elements have 4 and 4, we cannot have one more element having of size 4. So we cannot have, like, if we are saying that 3 elements have frequencies strictly greater than size by 3, that means their sum of frequency would exceed the size. This you can realize. So that means at max there can be 2 elements. At max there can be 2 elements which would give me a valid answer. So my answer would be either 0 elements, 1 element, or 2 element only. We would never have more than 2 elements having frequency greater than 1/3 the size of the subarray. Okay, so keeping this in mind, we can just store a vector of size 2 that would not add any great complexity. Order of 2 complexity is fine, it is order of 1 only. So what we can say is, in a segment tree we can just store for in every node that for this particular range, what is my answer. Okay, if we think like that in every node we store our answer. So in order to answer queries for a segment tree, in order to build a segment tree, if you can merge, if you can somehow find a way to merge 2 child nodes to get the parent node, then you can always write the answer. Okay, so if you can merge these 2 nodes, so this node stores your answer for the range from, let's say, L1 to R1, This stores our answer from L2 to R2. Now, whenever we are merging two range into a single range, we know that these two childs would be consecutive. That means this L2 would be just after R1. So this L2 would be basically R1 plus 1 only. Okay. So we have in an array, we have, this is L1, this is R2, this is R1, and this would be L2. So we would have a range from L1 to R1 and L2 to R2. We need to merge these two ranges into a single range from L1 to R2. So the parent would have a range from L1 to R2. Okay. Can we merge these two ranges of our segment tree? So if we know the answer for this range and if we know the answer for this range, can we conclude something for the answer for this complete range from L1 to R2? So think, if we know that there are like two elements, x1 and x2, which are like the majority elements in this range, which are the answers for this range having frequency greater than size by 3 plus 1, which have the frequencies greater than 1/3 the size. And if this also have some elements, let's say y1 and y2, which have frequency greater than the size, then for this resulting range, apart from x1, x2, y1, y4, there can any other element be the answer for this range? Just think about it. If I'm telling that for this whole range my answer is z, can I say that this z would be one of these four only? Is it possible that we have an answer which was not the answer for this child range? So if you think that, let's say yes, this is our answer which have a frequency greater than the size of this complete range by 3, then if you look at the smaller ranges, so if you like change the condition to, here the condition is frequency should be greater than frequency should be strictly greater than size by 3. We can change it to whenever you, if you want to check for x, if you want to whether x is the majority element or not, then you can say whenever you get a x, add a +2. Whenever you don't get a x, add a -1. So this way, if whatever is the frequency of x, that gets a double weightage, frequency of all those other elements gets a -1 weightage, then the sum of that weightage, if that sum is greater than 0, then we can say that x is a majority element. These two conditions are the same. If you think that if its frequency is greater than size by 3, then that frequency multiplied by 2 should be more than the remaining frequency multiplied by 1. Then only that frequency is greater than 1/3. So that means if I'm telling that this z is a majority element, then wherever this z occurs, if I'm telling that wherever this z occurs in this range, if you do a +2 here and a -1 in the remaining part, if that overall sum is greater than 0, then for the individual parts also, if I'm telling that both of the individual parts are less than equal to 0, then our overall part cannot become greater than 0. For the overall part to be greater than 0, at least one of the two parts should be greater than 0. That means we can say if z is the answer for this parent combined range, then z has to be the answer for at least either of this range or that range. That means whatever are the possible answers for the two child ranges, the answer for this parent range is one among those only. So in the child, always you would have at max two answers. Here also at max two answers. So in the parent, we just need to check for at max four possible answers. If you check all the four of them, at max two of them would satisfy it. So that you can update in the parent array. So in order of 4, you need to check 4 times basically at max. And how do you check it? That is the next problem. So if you can some way optimally check whether what is the frequency of some element x in the range from L to R. How do you check whether some x can be my answer? If you can compute the frequency of x in the range from L to R, then you would, if you have the L and R, you would get the size of the range and you would compute the threshold, which is psi 3 plus 1. And if this frequency of x in the range L to R is greater than the threshold, you can say this is my possible answer. Check it for all the 4. So the only task here is, can you check what is the frequency of x in the range from L to R? For that, what we can do is we can just pre-compute. You want to, we can pre-compute a vector for every x. So position of x denotes the list of positions where the element x occurs. Okay, so if you convert this array into a position vector, where position of x gives me the list of indices where x occurs, then we can check if we want to check the frequency of x in the range from L to R, we can write this function that check in this pos x list which is the position just greater than R, which is the position just greater than L. Okay, let's say this is the position just greater than L, position just greater than R. Their difference is basically the number of elements which are in between the positions L to R. So using upper bound, you can check if this is a sorted list of indices. So we can, while adding to the position vector, it would be, if you are moving according to the indices from 0 to n, it would be sorted. So in a sorted list, using upper bound, you can check how many elements in the list are in between L to R. That you can check in log n time using upper bound or binary search on this pre-computed vector. So this frequency check can be done in log n time. So then we can say that we can merge the answers for these two in 4 into log n time. Okay, so 4 into log n would be the time for merging two, and the querying in a segment tree would take me log n time. So overall q into log n into log n, okay, would be my overall time complexity. This would be 4 times log n. This for segment tree also, this log n is also a bit heavy, so it would have a bit heavy constant. So it's q into log n square with a bit heavy constant. So if you look, n and q are 2 into 10 to the power 5, so it's actually 2 into 10 to the power 5 multiplied by log of 10 to the power 5 is approx 20 or less than that only. So 20 square with a little heavy constant, so it would be 8 into 10 to the power 7, and we have a time limit of 4.5 seconds. So even a constant of like 4 or 5 times is also fine. Okay, so with this a greater time limit, these many operations would be fine. So this complexity would be acceptable. Okay, so I hope this logic is clear to you. Okay, so let's look at the code now. So we take the input, first of all, take the input array. We create this position list. Okay, so basically, in order to compute this frequency in log n time, we want this list of positions for every x. So we take this, we are declaring this as global because I'm writing a frequency function using this position map. So I'm declaring a global map of position, which I'll update for every test case. Now I'll clear this position first, because if I'm going to the next test case, I should clear out the global variables first. So I'll clear this position map, and then I'll iterate through every value in my array and update position of AI dot pushback I. Okay, this PB is pushback. So this is a loop from 0 to less than n. So for every AI, I'll push back I in the position map of AI. Okay, this way my position map is updated. Once my position map is updated, I've written this function to compute the frequency of any element I in the range from L to R, which is basically upper bound in the position I vector for R minus upper bound in the position I vector from L minus 1. So this, the difference between these upper bound would give me how many elements in between L and R occur which have a value equal to I. We get the frequency of I in the range L to R. Okay, so this thing is done. Once this log n function, we can write a log n function to calculate the frequencies. Now we create the segment tree. Okay, so I'm using this segment tree. So I have this template for segment tree. I just copy pasted it. So here I only need to update this node. I create a struct node. In every node of the segment tree, I'm storing three things: my L, my R, so the L and R for the range that this particular node is specifying, and this is a vector of int V, which is storing the list of answers for that node. Okay, now this I'm specifying default for an empty node. I take default value of L and R as -1 and empty V. And if I have to update the base node, initial node, then I'm passing I. So both L and R would be equal to I, basically the leaves of my segment tree. So leaves of my segment tree would have a range from I to I. That would be just one element, and that one element would be my answer because size of the range is 1, and that element only has a frequency of 1 satisfying the threshold. So this is what this struct we have created for updating my segment tree, and this function I've written for merging two nodes in the segment tree. Okay, so this A is my left child, B is my right child. Okay, so if any of the childs is null, basically I am combining with a null child having size 0, it would have L of -1. Then I just return the other child. If left child is null, I return right child. If right child is none, I return left child. So this base thing is covered, because in my segment tree templates, many a times when the range doesn't come in the range, then I take a null node. So I've specified that null node is -1. So that's why I've written this, but let's ignore that you can manage according to your template. Now I write my answer node. So in the merged parent node, its L would be the L of the left node, and its R would be the R of the right node. Okay, first thing is this: its L would be L of the left node, and R would be R of the right node. Okay, so L and R are updated, and then my threshold would be R minus L plus 1 is the size of the range. Floor division 3 plus 1 is my threshold. If any of the element has a frequency greater than or equal to this threshold, it would come in my answer. Okay, then I'll iterate through every element which were answers of the left node. Okay, so in V vector, I'm storing the answers of a node. So A is my left node. A dot V stores the answers for my left node. So in A dot V, I iterate through all the answers of the left node. If the frequency of I in the range from L to R is greater than equal to T, I insert that in my set. Same way for the right node, I check for all the answers in my right node. If its frequency is greater than equal to T, I insert into the set. Now in this set, I have unique elements which would be at max 2. I push all the elements in the set in the vector of my merged answer node. This way I update my answer node. So this way I have written the merge function for my segment tree, and according to this, my segment tree is created. Build of the segment tree, the build function, the query function. Okay, this query true is not required. This update function. Okay, update and query are required. Now, where we in the main function? So till here we had computed the position map. After that, I'll create the segment tree. For every index, I'll update my segment tree for I as node I comma AI. So this way I'll update the leaf nodes with a value AI. Okay, once leaf nodes are updated, then for every query, my answer is just segment.query L minus 1. So this L is 1 based index. In my segment tree, I'm storing 0 based. So I do L minus 1 is the 0 based index. And in the query function, left range is included, right range is not included. So this is actually R minus 1 is the 0 based index plus 1, because basically this R is not included in my range. So I need to include that. So that's why I get R. So if I do the query, whatever is the dot v, that is basically my answer. Okay, and if the answer dot size is 0, then I see out -1, otherwise I see out answer. This answer is a vector. This answer is a vector. So, but I have like I have defined the operator cout operator to output stream to print a vector space separated if I write it in cout. So you can just run a loop and cout it, no issues. So okay, so I've directly written cout answer because I have in my template only I have updated my cout to print it space separated. But you can run a loop and print space separated answers. Okay, so this way I answer every query in log n square time. Okay, so if you look at the time complexity, this loop input loop is taking n time. Okay, then this loop is again taking order of n time. Okay, this updating the segment tree would take again order of log n time. So overall n times log n would be n log n. Okay, for every query, this query takes log n time in general, but the merge function is also a log n time. Merge function is also taking, since using this log n time for the merge function. So this merge function is taking log n time. So this overall query would take actually log n square time. So we can say that we are answering all the queries in q into log n square. Okay, so overall time complexity is order of n log n plus q into log n square. This I can say is my overall time complexity, which is just accepted for the given constraints. Like my summation took around 4 seconds almost. Okay, let's save it. So my summation took almost 4 seconds and the time limit was 4.5 seconds. So it was just acceptable in the given time limits. Space complexity is you are using just array of size n, and this segment tree that you are creating, that would be of size 4n. So 4n you can say is my space complexity. So order of n is the space complexity. Okay. So I hope this problem is also clear to you. Is there any more doubts you may ask, or we can end the stream if all the problems are clear? Okay, so I guess it is clear to you, so we can end the session. Okay, so thank you so much guys. Thanks for tuning in. Goodbye.